Hello again, classmates. What we're looking at is we're looking at the sinusoid waveform for an AC voltage. This particular voltage would be relevant to North America, Canada, the United States, and Mexico. Compared to a battery or compared to DC voltage, and let's say we have 120 volts DC. Okay, this would be an AC waveform that would produce the same heating power that 120 volts DC would produce. And if you look in the lower right-hand corner of our sketch, you will see voltage with a subscript RMS is equal to 120 volts. Now this voltage is constantly changing. I have chosen to pick 0 volts as the starting point. The voltage climbs up to 169.7 volts. Then it begins to decline and it reaches the 0 volts line again. And then it swings into the negative voltage zone and finally goes down to a negative 169.7 volts, and then it swings back up to the 0 line again. So what we say this is, we say this is an AC cycle. An AC cycle or an AC waveform or an AC sinusoid. We say sinusoid because we mean that it has the sinusoid shape. In trigonometry, that would be the sine. For North America, and we're looking at a cycle here. For North America, we get a cycle 60 times per second. And what we say is that is the frequency of our AC power. So at the bottom of the sketch here, you will see that I'm showing that the frequency is 60 hertz. Okay, and hertz is simply a unit that stands for cycles per second. So what we have here, and this is where we're going to start, we have an AC waveform that is for an RMS voltage of 120 volts. The peak values of this sinusoid are 169 and negative 169 volts. The frequency is 60 hertz. And I want you to notice that right above the frequency, I mentioned the period. So the period of this sine wave is 1/60th of a second. And I believe the decimal for that is, let's see here, since I'm lazy and have to use a calculator for everything now. Yeah, the period is 1/60th of a second, or 16.7 milliseconds. So that's the basis of AC voltage. Okay, we also have AC current, and we have some redundancy here in the fact that AC stands for alternating current, and it is different from DC because it is continually alternating. Okay, this is my rendition, freehand, of a sine wave. Not great, but for purposes of discussion, we'll go ahead and use it. So I have a vertical scale, I have a horizontal scale, and this represents what is happening with voltage or amps or watts. It depends upon what we're talking about at the time. If we were to use an oscilloscope, an oscilloscope would plot this picture for us almost instantaneously. And I suppose it would look better than my sketch, but let's use my sketch. What do you say? So this is an AC sine wave. Okay, and let's say we're talking about volts. So we're starting at 0 volts because I just randomly chose that or arbitrarily chose that. And my voltage starts to climb and it gets to a maximum, okay, of what we call the positive peak of a sine wave. And as time progresses, that sine wave begins to decrease and head toward the 0 line, and this is the 0 line right here. And maybe I should write that. So let me get my red marker here, and we'll say that point right there is 0. Okay, so again, my sine wave starts at 0, it begins to climb, and it reaches the positive peak. This is 0, let's say we're talking about volts, 0 volts, maximum positive voltage. Then the sine wave begins to decrease, and it reaches the 0 line again. It continues on into the negative zone. Okay, this is negative voltage below the 0 line. And the sine wave continues until it gets to the negative peak, in this case, negative voltage. Okay, and then it climbs back up to the 0 line, and we begin the same process all over again. And as far as voltage is concerned, current or power that has this instantaneous shape, this goes on continuously. If you were in a math class, you might worry, you might worry primarily about 360 degrees worth of sine wave. Okay, but when we're in the generation of electrical power business, this goes on continuously and we hope forever. So my sine wave has positive peak and a negative peak. Now then, if I look at this cycle, and this is one cycle, okay, the distance from the starting point to the end point of one cycle we call the period, okay, and that is the time required to complete one cycle. Okay, I think I've covered what needs to be covered. I'll let you look at that, see if you need to copy it or if you need to take notes. Please do so.